Okay, maybe again. Maybe just a different way your brain's seeing it than mine. It could be accurate. I will explain it this way. When you have a linear factor, you have a constant numerator that goes along with that. A is just a constant. It'll just be a number. When you have a quadratic factor, you have a linear numerator. So the numerator placeholder, I guess, is always 1 degree less than the denominator. We won't do cubic factors, and I've never explored this, but my conjecture, hypothesis would be if we had a cubic factor, your numerator that went along with that would have to be a quadratic, is my guess. If we have time, we can play around with it. But does that make sense? Okay, Stephen, do you have a question? Okay. So from here, we have to do the same thing, get a common denominator or clear fractions, whatever you want to do. I'm going to get a common denominator. I think I like that better. But it doesn't matter because it is the same thing either way. Thank you, Josh. This one needs an x minus 2. This one needs an x minus 2. So we can drop, drop, drop. So 3x squared plus 17x plus 14, and we have a little legwork to do on our distribution on the right. So we have ax squared plus 2ax plus 4a. Here we have to FOIL, yes? Binomial times binomial. So it's going to be a plus bx squared minus 2bx plus cx minus 2c. And then it's the same as it was yesterday, setting up those systems. So our x squareds are all supposed to combine to be what? 3. So 3 is supposed to equal an a plus a b. That's it for x squared. Our x's are all supposed to add up to be 17. So that's 2a minus 2b plus c. And our constants are supposed to add up to 14. So that's 4a minus 2c. So in solving the system, we want to take advantage of the fact that either the c is already eliminated or the b is already eliminated. It doesn't matter. I'll take advantage of the fact that this one, the c, is already eliminated. Oh, do you need a pass?
No.
Okay. The c is already eliminated in the first one, so I'll use the second two equations to eliminate the c there as well. So I need a multiplier of 2 on this guy. And I'll just line this one up without changing it. Oops, minus 2c. And then add or subtract. Add, opposite signs, add. Good. 34 plus 14, 48. 4a plus 4a is 8a. Negative 4b plus nothing is still negative 4b. So now I have a's and b's, a's and b's. So I'll just use a multiplier of 8 to get my a's the same. So times 8, we'll bring this down here. Subtraction, same sign on the 8 a's, so subtract. And b equals negative 2. Go back, what's a? 5. All right, if b is negative 2, add 2 to both sides, a will equal 5. And then if we know a is 5, 4 times 5 is 20. Subtract your 20 over, you'll get negative 6 equals negative 2c. So c equals 3. And then your actual answer will be 5 over x minus 2 plus negative 2x plus 3 over your quadratic. Oops, I just wrote all of that up here without having it on the screen, sorry. So just plugging in your A, B, and C to your original structure. That's an easy jump from yesterday, yes? Okay, so that's really it. And what we're about to do here will be the same thought process we did yesterday. So the factor in this denominator is this, x squared plus 1. But we have a multiplicity attached to that. So it's still a quadratic factor, so the numerator is still going to be linear, ax plus b. But the first time we do x squared plus 1, and the second time, now we have cx plus d, we up the ante and make it x squared plus 1 to the second power. Like we have to keep increasing that exponent. Like if it was to the third power, we would do it again to the third power and so forth, just like we did yesterday. But you have to look at that base and know that that is a quadratic factor, so it deserves a linear numerator. Any questions on that? Okay. So you would go through and solve that. I'm going to bypass that part. Here's my outlined, just generic format for this, which again I think is more confusing than it's worth. So I'm not going to over-explain that. I give it to you, but I think it's more powerful that I just showed you 2 examples of what I did. And then why don't you go through on your own and do the setup, just the setup for these 2 examples. And I'm going to prepare something that I want to show you. Raise your hand if you're done. Okay. Kyle, what was your setup for the first one? Good? Any questions on that? That's perfect. And then your setup on the second one, Zach. I missed your second part. A over x squared plus 1. What's the gallery think? Adam? Zach, does that make sense to you? He is correct. So if you look at this factor, is this a linear factor or a quadratic factor? Quadratic, so it deserves a linear numerator. And then you just, because that linear numerator leaves you off with b, you have the linear numerator on the second one, because that factor is still a quadratic. You're just kind of upping the multiplicity. So you had the linear factor there, which was good. But we had to start with c, or Adam started with c because he had left off with b already. Okay? That's really what the midterm question is going to be. It's going to be a multiple choice of what setup is appropriate for this problem. Okay? And so you won't have to actually go through and solve. Adam. No, you wouldn't. It only needs one x to get a common denominator here. Yeah. It only needs one more x squared plus 1. So this is going to need just x squared plus 1. This doesn't need anything. Okay? All right, so we may come back to that if we have time. But what I wanted to show you, and now that we have both days under our belt, is we solved this one yesterday, right here. This was our notes, and when we were talking about still a linear factor, but being squared, so our setup looked like this, a over x plus b over x minus 3 plus c over x minus 3 squared. So we were upping the multiplicity. And we did that, and we got this. Yes? Okay? So, Stephen had a good question as to why can't we just do a over x plus c over x minus 3, or plus b rather. Why would I jump right to c? Like this. I think it's a good question, right? Because who decided that we needed to up the multiplicity one by one by one? And so I played around with this and I went to solve it because I could, back to the original, I'm going to get a common denominator pretty easily. This one's just going to need x minus 3 squared. And this one's going to just need x. So x squared minus 6x plus 9, distribute your a to that. That's going to be ax squared minus 6ax plus 9a plus bx. Yes? So now my x squareds need to add up to be 0x squareds. So that's just a equals 0. My x terms need to add up to be 1. So that's negative 6a plus b needs to equal 1. Well, since a already equals 0, what's b? B is 1. And then lastly, your constants, which you just have 9a, needs to equal negative 18. Thank you. And you solve for a, and you get that a equals negative 2, and you have a contradiction because you already thought a was supposed to be 0. Do you see the problem? And the reality is, because this is the proper way to do it, this second a value is correct. But our b was wrong, and we have no c. So you'd get to this contradiction. It would be like, what do I do from there? Well, the b is wrong because we used the wrong a that we found, which was the initial a. If we had used this a to find the b, that would that have panned out? No, because a would have been negative 2. That would have been 12. 1 minus 12 would have been a b of negative 11. So that doesn't work, right? So I don't know how they ended up going this avenue with it, but they certainly realized if they kind of use this method that there's a contradiction and something isn't working out. So you can't do it that way. But now knowing what we know, if you do it this way, and you treat this as a linear factor, so a over x, and rather than treating this as a linear factor with a multiplicity of 2, if you treat it as a quadratic factor, I almost wonder if then So instead of using b, do bx plus c and treat this as a quadratic factor. Like a single, does that make sense what I'm doing here? Okay. I wonder if that would work out. So if I try this needs an x minus 3 squared. This one needs an x. And then I can drop. So again, this is still going to be ax squared minus 6ax plus 9a. And this one, when I distribute my b, is going to be plus bx squared plus cx. Now my x squareds are still supposed to add to 0, but I have 2 of them now. I have a plus b is supposed to equal 0x squareds. My x's are supposed to be 1, so that's negative 6a plus c is supposed to equal 1. And 9a is supposed to equal negative 18. So I do get a equals negative 2, which tells me, what does b equal? Positive 2. And so c will equal negative 6 times negative 2 is 12. Subtract 12 from both sides. 1 minus 12 is c equals negative 11. Are you with me? So the final answer under this structure is negative 2 over x plus 2x minus 11 over x minus 3 squared. Is that correct? You can't really tell because it's split up differently. Certainly they both have negative 2 over x, but this fraction is almost decomposed into those two fractions, so are they the same? Let's try to add these together, just these two, in C. So this one would need an x minus 3, and this one would need an x minus 3. So you get 2x minus 6 minus 5 all over x minus 3 squared, with the negative 2 over x out in front. And then you get 2x minus 11. Are they the same?
Yeah.
So I thought that was interesting. So you can treat a linear factor with a higher multiplicity of 2 as a quadratic if you want. Yeah. Because think about this if you hadn't factored it. It would be x minus 18 over x times x squared minus 6x plus 9. So you've got a linear factor and a single quadratic factor. So it should work. It should have no problem always working. Because we have time and I love to explore, I want to know about my cubic conjecture. So let me make up a problem. Oh boy, this is always new. Let me see if the book has a cubic one, so I don't, you see all the problems I run into when I have to try to make up a problem on my own, all these things, but it's a very good learning opportunity when you make up a problem and then try to find the right numbers to work. I'd lose half of you, so I'm not going to do that. But let me see if I can grab a cubic. Nice. Number 42. Oh, no. It's not going to work. I'll show you why. Well, maybe it will. So I think the book's intention is to take this x cubed minus 1, which is the difference of perfect cubes, and factor it into a linear and a quadratic. Okay? So you would split it up into a over the linear, a over the linear, and then bx plus c over the quadratic portion of that factorization. But what if I did this, and here's our new activity. Wonderful. I want you all to take this, 3x minus 5 over x cubed minus 1. I want you to factor that by the difference of perfect cubes and do what we practiced today and treat it as a over the linear portion and b over the quadratic portion. Haley, don't look at me like that. Let me get you started. When you factor the difference of perfect cubes, what do you get? Who can be an all-star and tell me? Jalen. which is just 1. Perfect. So you guys, I want you to treat it like this and split it up accordingly. In the meantime, I'm going to try my cubic conjecture and see if it's the same when you guys are done and when I'm done. I didn't really decompose anything. Look at what I just did. Because it's just a single cubic denominator, I just did a single quadratic numerator, and so I'm going to get A is 0, B is 3, and C is -5. So I just have the same problem I started with. I didn't decompose anything. I think I would need a second factor to test this. So carry on your way. Let me see if I can find a different example. Google should be good. Raise your hand if you got A equals -2/3. Okay. Yep, we'll get there. It's going to come up on tonight's homework. So good. I'm glad this happened. So you definitely don't want A, B, and C to be mixed fractions. And you'll see why in a second when we get there. So -5 minus 2/3 is like -5 2/3, which is -17/3. What are you saying? Oh, rats. Sorry. Thank you. Never mind that one. -2/3. For the record, oh rats was not a part of my vocabulary until recently when my son started saying oh rats. but I kind of like it. Add 2/3. So negative 5 plus 2/3 is negative 4 1/3. So C is 4 1/3, which is 13/3. Did you get that, Josh? Good. And then B, A plus B has to be 0, then B is 2/3. So how do you write that? So the A being negative 2/3, you'd put the negative 2 in the numerator and the thirds in the denominator outside of the x minus 1. Oh, did you? Good. The bx plus c, I gotta think about a little more here. Because, I mean, technically it would be 2/3 x plus 13/3 over that quadratic factor. So that's good. So since they both have the same denominator, I can just put the 3 in the denominator, and then the numerator will just be 2x plus 13. Get them to be the same, and then do the same thing. So if they're not the same, get them to be the same, and that takes care of that, so we don't have complex fractions. Wonderful. Okay, so with our remaining 5 minutes, sit back, look pretty, because I found an example that I want to test on the internet. So this particular problem that I have right here, on the internet, they treat it as a linear factor and then a linear factor with a multiplicity of c. So they have b over x minus 1, c over x minus 1 squared, d over x minus 1 cubed, and they work their way up. I'm not going to do it that way because I have their final answer, I hope, on there. I'm going to do it with the cubic conjecture that I had. So over the linear factor, x is still a. But I don't want to treat this as 3 different fractions. I just want to treat it as one denominator. And I'm going to use a quadratic numerator and see if I run into any trouble doing it this way, which I may. I have no idea. My guess is that it will work. You ready? This needs x minus 1 cubed. This one just needs x. I don't like doing x minus 1 cubed, but I know what x minus 1 squared is. And then multiplying it by another x minus 1 will give me x cubed minus x squared minus 2x squared plus 2x plus x minus 1 combines to be x cubed minus 3x squared plus 3x minus 1. So I'll distribute my a right away. So that'll be ax cubed minus 3ax squared plus 3ax minus a. And the second one I just need to distribute an x to. So plus bx cubed plus cx squared plus dx. Now my x cubes are supposed to add up to 0x cubes. So a plus b is supposed to equal 0. My x squareds are supposed to add up to 1, so negative 3a plus c is supposed to equal 1. My x's are supposed to add up to 0, so 3a plus d equals 0. And then my constant is supposed to just be 1, so negative a equals 1. All right, so we'll start there. A equals 1. A equals negative 1. Then we'll go up here, b equals 1. Then maybe we'll go here. So negative 3 times negative 1 is 3. Subtract 3 from both sides. C equals negative 2. And for D, plug in an a of negative 1, you get negative 3. You have to add 3 to both sides, so D equals 3. So according to my work, I don't have any contradiction, so I'm happy about that. My answer would be negative 1 over x plus x squared minus 2x plus 3 over x minus 1 cubed. just plugging back in here. Their answer is, they have a lot more work. 1 over x minus 1 plus 2 over x minus 1 squared. Oh no, cubed. Minus 1 over x. That's their answer. Do we think they're going to be the same thing? Well, I like the fact that this already checks off. I would just need to get a common denominator on these two to see if they combine to be that. I think it's going to work. It's the same thing that happened last time. So if I do x minus 1 squared, I think it'll work. Okay, your midterm. Period 2 is in room 201. Thursday. Yes?
Yeah.
Thursday morning, 7:35. Room 201. Okie doke.
How many questions?
This homework is due the day we get back. How many questions? 50 questions. 50 multiple choice. Okie doke. You will have a trig reference sheet. Use all the review packets chapter by chapter online for multiple choice. The multiple choices are not going to be strangers. They're either in the review packets or they've been on tests, so that there's nothing that will look brand new to you, except for the one partial decomposition question.
Is the trig thing going to be filled in?
No, the double angles you still have to know.
Well, all the other ones.